question, what is a vector? A vector is a line segment with two special attributes. We will examine two attributes common to all vectors. A vector has magnitude, which is a fancy word for size or length. And secondly, a vector has direction. We're going to look at a vector and observe these characteristics. Here's a drawing of the first vector we'll look at. This is what a graphed vector looks like, an arrow. We'll call this vector vector u. Vectors are often named as lowercase bold letters. Sometimes you'll see the vector written as a bold lowercase letter with a little line segment over it. Instead of a line segment, it can also be a little arrow over the letter. And we place the coordinates of vector u as 7, 6. Note that instead of parentheses surrounding the coordinates, we have angular brackets. The angular brackets signify that this arrow is a vector. Alternatively, vectors can be labeled by the starting and finishing point letters with a little arrow on top of the letters. This is the same vector as u, but labeled vector PQ. Back to the vector labeled u. The ends of the vector have names. The finishing point of a vector is called the head or tip of the vector, and the starting point of the vector is called the tail of the vector. How can the magnitude or size of vector u be determined? To determine the magnitude of a vector, we can use the distance formula, which is a coordinate plane application of the Pythagorean theorem. We can also determine the magnitude of the vector by separating the vector into the legs of a right triangle. This vector has a horizontal component of 7, which is the base of the triangle, and a vertical component, which is the vertical leg of the right triangle, of 6 in length. And here we have entered in the calculator the square root of quantity 7 squared plus 6 squared. We press enter and find our magnitude. The magnitude is about 9.22 units rounded to the nearest hundredth place. And so we now can label the vector with a magnitude of about 9.22. This vector u can be resolved into horizontal and vertical component vectors, and here the horizontal and vertical components are drawn as component vectors. The horizontal component vector can be labeled u sub x with this little x to the right of the u, and the vertical component vector can be labeled u sub y. We can also use the bracket numerical notation. The horizontal component is 7, 0 in brackets, and the vertical component is 0, 6 in brackets. What we have done here is resolve the vector into horizontal and vertical components. This is called a resolution of a vector. These are also called rectangular components of a vector. Now we'll turn to the second characteristic of a vector, its direction. There are a lot of ways to express the direction of a vector, so many that we certainly will not handle all of them in this video lesson. But to start out, we'll call this angle symbolized by the Greek letter theta the measure of the angle rotated up from the positive side of the x-axis. If this topic is where you are in a pre-calculus or trigonometry course, the way to determine this angle should be pretty fresh on your mind. Since we have all sides of this right triangle now, we can use any one of the 6 basic trigonometric ratios to find the angle that describes or quantifies this direction. Just to pick one ratio, we'll use the information we had at the beginning, the knowledge that the opposite side of angle theta is 6, and that the adjacent side, the bottom of the triangle, is 7. Therefore, the tangent of angle theta is the fraction 6 over 7, or 6/7. Therefore, the angle theta equals the inverse tangent, or arctangent, of 6/7. Some of my students like to call this tangent -1. We can enter this expression into our calculator as shown. So after checking our calculator, make sure we're in degrees mode and not radians. When we press enter, this is what we get: 40.60 degrees rounded to the nearest hundredth place. And here the measure of angle theta is labeled as approximately equal to 40.60 degrees up from the horizontal. Now we'll do something else. Let's look at this second vector, the vector labeled v. All we have here is a vector with magnitude and direction. We don't even have coordinate grid squares with which to work or compare. This is vector v that has a magnitude of 10. The vector is also elevated from the x-axis at the left at an angle of 60 degrees. What we'll do with this is called resolving the vector. It means to break a vector into components, into x and y components. Sometimes you'll hear these components called rectangular components. The x rectangular component is found by multiplying the magnitude of the vector by the cosine of the direction angle. So the x rectangular component, which we call v sub x, is the magnitude of the vector 10 times the cosine of the angle of direction, which will be the cosine of 60 degrees. Maybe you know that the cosine of 60 degrees is 1/2 or 0.5, but in case you don't remember that, here the numbers are entered in the calculator. And pressing enter, we find that v sub x equals 5. And so we make the notation that v sub x equals 5. So we draw in the rectangular component v sub x equals 5. But looking at the drawing in of the vector, does this make sense? V sub x goes away. It's to the right of vector v, whereas the vector v is pointing toward the left. Well, no, it doesn't make sense. Vector v sub x is going to the right. The vector v sub x should go to the left. The problem is that angle alpha is not really 60 degrees. This angle, starting quadrant 1, is really angle alpha 120 degrees. So instead, we really have v sub x equals 10 times the cosine of 120 degrees. And here is 10 times the cosine of 120 degrees entered in the calculator. Press enter. This time we see that v sub x is negative 5 units in magnitude. And so this is the component vector v sub x just going to the left instead of to the right. Looking now at the vertical component vector, we have v sub y equals 10 times the sine of 120 degrees. And we place this expression into our calculator, press enter. We get about 8.66. This is really 10 times the square root of 3. So we write v sub y is approximately equal to 8.66 units in magnitude. And we can now draw the vertical component vector v sub y. These items we call rectangular components. We've gone over elementary terminology on vectors. Next we'll go into some real-world uses of vectors with examples that show how they can be useful. There are many uses of vectors, but we'll just look briefly at 3 of them in this lesson. First, we'll look at the use of vectors in determining and describing forces. Then we'll look at the use of vectors in navigation. And finally, we'll look at the use of vectors in describing projectile motion. First, let's take a look at me sitting on the piano bench at home while creating this video lesson. The weight of my body is 190 pounds, and it's attracted toward the center of the earth by gravity and exerts a 190-pound force on the piano bench. This downward force can be represented on a coordinate plane by this vector, an arrow pointing downward. We'll call this vector W, and it's numerically represented by 0, negative 190 enclosed within angular brackets. But to keep me sitting on the piano bench, there's another force at work as well, and that force is described by Newton's third law of motion. When a first body exerts a force F sub 1 on a second body, the second body simultaneously exerts a force F sub 2 equals negative F sub 1 on the first body. This means that F sub 1 and F sub 2 are equal in magnitude and opposite in direction. And what is this force keeping me in place? That force from the piano bench upon which I'm sitting is upwards and is represented by this green upward arrow, so it's pushing up on my body weight. This new vector represented by the green arrow will be called vector P, and it is numerically represented with 0, 190 within angular brackets. To find the net effect of these forces, we add vectors W and P. we add the numbers like this below. Here they are separated by a plus sign. The vector representing their sums will have an x value of 0 plus 0, which equals 0. And the y value of the vector will be the sum of negative 190 and 190. So the sum of these two vectors is 0, 0. This is what we call an algebraic method of adding vectors. Another way we can add vectors is to do so graphically by placing these vectors head to tail or tip to tail. And we see that the net effect is the same, that the sum of these two vectors is a vector described as 0, 0. This is an almost absurdly simple example, but in engineering we can use the same principles to support bridges and other structures to account for forces or likely forces on structures to be certain these structures are supported to where they are stable. This is called a graphical representation or method of adding vectors. And we box in our answer that vector W plus vector P equals 0, 0 in angular brackets. Now we'll look at another use of vectors, navigation. You'll often see this in plane flights, how the prevailing winds change the speed and direction of flight. You can also see this with boats reacting to water currents. For this example, we'll have a plane flying northward at a speed of 500 miles per hour. What would be the plane's speed and direction if the plane encounters a west wind blowing at 50 miles per hour? Here is the vector representing the plane going north at 500 miles per hour. We call this vector P, and the numbers we use are the coordinate pair 0, 500 inside angular brackets to represent a vector. And from the west we have our wind vector. We call this vector W and identify it by the ordered pair 50, 0 placed within angular brackets to signify that it's a vector. Graphically, we can move the tail of the vector W to the tip of vector P, and with these two vectors added together tip to tail, we have the vector P plus W. And this new vector is vector P plus W. The numbers representing this vector are 50, 500 within angular brackets. And to find the magnitude, it's the Pythagorean theorem again, the square root of quantity 500 squared plus 50 squared. Press enter. We get a magnitude of about 502.5 miles per hour. So we can label the magnitude of the vector P plus W. And we want to find the angle of the plane will be moved away from the north heading, so we will label the angle we're looking for as theta. And in this right triangle, the opposite side of the angle theta is 50 miles per hour, and the adjacent side of this right triangle is 500 miles per hour. And using the tangent ratio and the inverse tangent relation, we get theta equals the inverse tangent of 50 over 500. And here it is entered into the calculator. We press enter and get an angle of approximately 5.71 degrees. And finally we describe the angle in terms of direction, and that's east of north. And we box in our answers as correct. The reason we could use the Pythagorean theorem was because the wind vector was horizontal. If that wind vector had not been horizontal, we would have had to use the law of cosines. And we'll tackle that situation where law of cosines is required in an upcoming lesson. Now we come to our third use of vectors in this lesson, projectile motion. In launching an object, we can take a close look at an initial angle, which we call the angle of incidence. Now this blue ray designates the initial firing or launching magnitude and direction of the object. And the coordinates of this vector are 5, 11. Now to analyze this direction and magnitude, we will measure the drawing of the ray against the coordinate grid shown here. As I mentioned earlier in this lesson, there are other notations available to show that a line segment is a vector. I've seen it in angular brackets like this. A vector, again, has two attributes, magnitude and direction. In fact, that's a definition of a vector. Its quantity has both magnitude and direction. Magnitude, again, is another word for length. And on a coordinate plane, it has another definition. Again, A vector is an ordered pair whose geometric representation is an arrow. This vector can be separated into vertical and horizontal components. The vertical component is 11 units up, and the horizontal component is 5 units to the right. To find the size of this magnitude, we find the length, and to do that, we can use the Pythagorean theorem. So we would find the magnitude by taking the square root of 5 squared plus 11 squared, and that's a little over 12, about 12.083. If we knew the angle of incidence from the horizontal, we could use trigonometry to rewrite our vertical and horizontal components of the vector. The angle of incidence happens to be about 65.556 degrees. I found this angle, as shown in the calculator screen image, by taking the inverse tangent or arctangent of 11 over 5. And now with a magnitude of 12.083 and an angle of incidence of 65.556 degrees, we can rewrite the vertical and horizontal components of our vector as follows. The vertical component is 12.083 times the sine of 65.556 degrees, and the horizontal component is 12.083 times the cosine of 65.556 degrees. Now we'll conclude this beginning lesson on vectors by looking at some fairly simple problems involving vectors. Problem 1. Below is the drawing of a vector representing the force from gravity on a 5-pound brick. Which of the vectors in the answer choices is needed to support the weight of the brick? The correct answer is B, the vector 0, 5. Problem 2. Vector u and vector v are shown on the coordinate plane below. Which of the answer choices represents vector u plus vector v? The correct answer is D, the vector 6, 0. We can place vector v tip to tail with vector u and see that the end or tip of the relocated vector v ends up at the point 6, 0. Problem 3. A plane is flying at a heading due north for 600 miles during 1 hour. During the flight north, there is a 100 mile per hour wind blowing to the east. After 1 hour, how far is the plane from its starting point? The correct answer to this problem is D, 608 miles. Since vectors u and v are at right angles to each other, we really have a Pythagorean theorem application, and the calculator shows that numbers worked out to be a little over 608 miles, which is closest to answer D. Problem 4. For vector u shown below, what are its component rectangular vectors? The correct answer is A. Vector u sub x is 3, 0, and vector u sub y is 0, 9. Problem 5. For a vector representing a ship traveling to the southwest, where will the tip or head of the representative vector be located? The correct answer is C, quadrant 3, as shown in the drawing. This has been Vectors 101. Thanks for viewing.